Welcome, everybody. This is the first session of Before Developer Days of the Years, and the presenter is Aristide Akem, lecturer at the University of Southampton. This session is recorded and will be available on before.org website and YouTube channel together with the slides. At the end of the presentation, the people from the audience can ask questions. And the title of the presentation of today is In-Network Inference with P4, from stateless to hybrid approaches. And Aristide, the floor is yours.
Yeah, so thank you very much, Davide, for the invitation, first of all, and for this opportunity to be able to talk about my work. And thank you to everyone as well who is in the audience, who has come to listen to this talk. So this work would be work that has been done over the last 4 years, I would say, 4 to 5 years, from when I started my PhD, all up until now that I finished and then did a postdoc and then now started as a lecturer in the UK. So a brief outline of the presentation. I'll begin with a background on network machine learning inference, how we got here in the first place. Then I'll narrow it down a little bit to focus on in-network inference and switches, which has been where the bulk of the work has been done so far, until much recently, where we have a lot of work as well being done on smart network interface cards and other emerging targets. And then I'll try to trace now the path that we followed from where we all started with the stateless approaches, which are more intuitive based on the fact that these devices are meant to process packet after packet. And then I would go to the stateful ones, which are more challenging because of the need to maintain state. And I'll end with the hybrid approaches, which kind of offers the best of both worlds by combining the benefits of both the stateless and the stateful approaches. Then I'll conclude and talk a little bit about what we are currently doing and what we think the next steps would be regarding this work. So I'll begin with this quote. And so I found this online when I was looking at quotes about network programmability and network automation. And this is something Nick McKeown said in 2012 during the question and answer session. So he talking about network automation, he said there will be a time when there will be less need for people to make the network work on a day-to-day basis because it will be more automated. And he said he thought that there will be far more things that we can do with the network. So there will be a massive increase in people programming the network. And just a few years after he said this, then there was the advent of P4, and then there was the advent of many programmable network devices, and that has spurred a lot of interest in network programmability to facilitate the automation of network management in general. And among these different aspects of the network that have been programmed, some of the applications that have been inspired would be in-network machine learning. And when we talk about in-network machine learning, just to offer a background here, we are talking of machine learning models that are running for inference within the network entirely, okay? So just to clarify at the beginning that we'll be talking specifically about inference. So in all cases, for the entire duration of this talk, the models would have been trained online and we will only be doing inference within the network. So we are not doing in-network training. Of course, there is work that uses networking devices for in-network aggregation to be able to help in machine learning training workloads, but that's beyond the scope of this talk. So if you look at the red arrows, you'd see that traditionally with machine learning systems that were used for network automation, typically we would have some machine learning server that is either external to the network or is in the control plane, which will receive samples of data from the network, analyze them, and then perform inference on them, and then send insights back to the networking devices, which could then act on those insights to forward traffic. But this back and forth communication between external servers or control plane servers and the data plane led to latency that could be up to hundreds of milliseconds, which would be undesirable in ultra low latency applications where we want to be able to perform sub-millisecond inference. So with the advent of programmable network devices and need network computing, this paradigm of in-network machine learning came to be, whereby we are looking at ways in which we can embed those machine learning models directly within the network equipment so that we can perform inference on traffic as it goes through the network without having to offload some of this traffic to external servers. And the benefit here is, of course, that we are able to eliminate this back and forth interplane latency, and we're able to perform high-speed inference with very low latency and very high throughput. And a lot of the use cases that we've seen so far are in the areas of cybersecurity, traffic engineering, advanced routing, and a lot more. So, like I mentioned, we are focusing on inference, which means that the entire training process of the models, be it feature engineering, designing the model, training the actual model, which could be anything from tree-based models like random forest to neural networks or their binarized equivalent, all of this happens offline. Then once we have the model that has been trained, we can then use a network programming language or domain-specific language like P4, which is what is bringing us together today, to encode the model that has been trained into a P4, into a program that can then be executed on a programmable data plane target, which could be anything from a switch to an FPGA to a smart NIC or GPU, IPUs, or any other kind of device as you have them today. Once the model has been deployed on this device with the domain specific language program, then traffic flows that are going through each of those devices can then be classified or inferred upon using the model that has already been deployed on these devices. And these different approaches already exist in the literature. So for example, for approaches running entirely in the switch, there is a popular paper Planter, which basically came up with this, proposed some of these concepts to deploy stateless models within programmable switches. Then in cases where we have programmable switches augmented with additional devices for computing power, such as FPGAs, we have examples like Taurus, which exist also in the literature. And for cases where we have models running entirely on smart network interface cards, we also have other examples existing like the N3 IC. So these are early works that kind of preceded most of the work that we did in this space. So most of the work that has actually been done in this area have focused on programmable switches. And in the next section, we'll be looking at why programmable switches have been the focus of most of these works. Well, it's kind of intuitive because you would have a switch almost at any point in the network, which is why we say they have an ubiquitous presence in the network, because everywhere in the core of the network, you're going to find switches, be it at the core or even at the edge sometimes, to interconnect different parts of the network. So if we can convert all of these switches into inference engines, we are potentially leading to intelligence everywhere in the network. In addition, these switches have so many ports. So if we have 3200 gigabits per second ports, we are talking of 3.2 terabits per second already. And then if you look at the fact that it's full duplex, we're talking of already maybe 6.4 terabits per second and things like that. So they bring us very low latency and also very high throughput. This is why switches have been the main point of attention in this area of in network machine learning inference. But of course, we also have some limitations when we are dealing with these switches, or rather, let me call them constraints, because they are not limitations per se, since they are design choices. So because of the nature of these devices and what they are meant to do, which is to process packets and forward traffic, the amount of memory that is available, because it's expensive memory like TCAM and SRAM, is usually not in large quantities. So the amount of things that we can do on these devices is quite limited. And of course, the support for mathematical operations is also limited, as well as the number of operations that we can do per packet, coupled with the inherent constraints that we also have in programming languages like P4, which we are using to program this equipment. So the main question here that we've been answering while working on all of these solutions for these different targets has been, how can we accommodate all of these constraints and still be able to efficiently deploy models on these equipment for high-speed inference for different network applications? And one of the simplest responses, that came was to use models that are more adapted to this kind of hardware. And that led us to turning our attention to tree-based models for in-network inference. And we from the different analysis that we did at the beginning of these works, we found that tree-based models were the most appropriate for in-network inference. And the reasons we give here are twofold. So the first one is intuitive. The fact that the logical structure of a tree-based model is very much like or let's say very analogous to the pipeline that you have in the switch. So if you look at a tree that we have at the bottom of the screen here, usually you would just check a certain feature threshold, and that tells you whether to go left or right. And you can continue checking until you get to the corresponding leaf node, which tells you to what class that particular sample belongs. And that's a similar thing you would have in a PISA pipeline, like what you have in most of the programmable network devices, where you match a certain condition, and based on the result of that match, you then decide on what action to take. So the match and action paradigm becomes similar to what you have in a tree, like just checking a condition and deciding where to go. So this analogy between the two structures makes it very easy, or let's say easier, for you to map tree-based models to these kind of pipelines. And then recent work also showed that, meaning the deep learning and machine learning community, that when you have structured data that are in tabular form, like most of what you would have for many of the networking use cases where you're just doing packet classification, in such cases, tree-based models often outperform or are on par with even more complex models like a deep learning model. So if we have these two reasons in mind, then there is a strong motivation for why to focus on tree-based models for in network inference, which is what we've done for most of the solutions that we proposed. So well, with that said, let's look at the pipeline. So what's the workflow that we would typically follow when we are trying to implement models in the switch or in any other programmable hardware target? We mentioned that because of the fact that we are only doing inference in the data plane, every other aspect related to model preparation and model training will take place in the control plane or in some machine learning server that is out of the network. So typically we would get these data sets as packet captures, which is the best form, like I said, so that if you want to replay these packets through the programmable network device, it would be straightforward to just replay the packet capture. And then we would extract different features and compute statistical features if we are doing, if we want to also get some statistics from the features that we've extracted in the case of stateful inference, or we could just use the packet headers themselves. And we'll typically extract all of those features using tools like Wireshark, T-Shark, or Python, and we would get fields like packet headers, be it from the IP protocol or the transport protocol layers. And in addition to this, we could then compute statistical features based on each of these. So in addition to the packet length, if we're doing stateful classification, you could also have statistics on the packet length, like the standard deviation, the variance, the mean, the sum, maximum, minimum, total, and all of that. Same for the other features that we extract. And then once we have all of those features, we can then do our model training and optimization, which is also offline. And typically we use scikit-learn libraries, depending on what model we need. And then we could proceed with also some feature selection and optimization techniques, as well as other feature compression techniques that I'll mention when we are talking of some of the specific solutions. So once we have our trained model, we can then proceed to map the model onto match and action tables that will be implemented in the data plane. So here I show you a simple structure for map, or a simple approach to map a tree-based model to match an action pipeline. And this approach is the approach that was originally proposed by Planter, where you have feature tables and code tables. So for every feature that you have in the model, you're going to extract all the different thresholds that belong to that particular feature, and you place all of them in a table, and you establish ranges between each of those thresholds. For each range, you're going to assign a code word. And so when the sample comes and you extract its value for that feature, you match on this table. Depending on the range where it falls, you assign a code. And then when you concatenate all the codes that you get from all the different feature matches that you've done, it generates a code word, which you can then map by a ternary or exact match, depending on the approach that you use to get the final label of that particular sample. So this is basically one of the approaches to map. There are other approaches where you can do direct match, where you simply map each layer of the tree to one match and action table. But most of the solutions that we propose were based more on structural designs rather than on the actual mapping. So most of the solutions that we have, you can replace the mapping with anyone that you want. So it's quite flexible, but this is just one of the main approaches which has been used by majority of the works. So Then once you have this model converted into match and action table entries, you can then load them onto your controller, which at runtime will inject them into the programmable match and action pipeline. So here we have a programmable match and action pipeline similar to the pizza architecture, but more like what you would have in Tofino. So when your packet comes in, then it is parsed, you extract the different headers, your packet goes through the match and action pipeline where you execute all the tables that are representing the model, and then you can get a classification result. Then you can also do additional processing in the egress pipeline, and then the packet is finally packaged and sent out at the end of the pipeline. So globally speaking, this is how the in-network machine learning inference pipeline would look like. So now let's get to the core of the talk, which is basically looking at how we've transitioned from stateless approaches to hybrid approaches. So with the stateless approach means that we are not storing anything. So we are not keeping any state. So we are dealing with every packet as it comes. And this is the most straightforward approach because as a packet comes, just like you would normally forward packets using a simple routing table. When the packet comes, you extract headers from it, you perform a lookup on the routing table, and then you decide where to send the packet. So similarly, if we've already encoded our model in this, if we've trained a stateless model and encoded it in the match and action pipeline, when the packet comes, you extract the headers, which in this case are your features. You match them on the different tables that have been used to encode the model, and then you assign a class, and you can forward the packet based on that class. And this is quite intuitive because generally these network devices are made to process packets one after the other. So if you can use this same paradigm to classify packets, then that's actually very natural. And one other advantage you would have is that since you're processing every packet independently, then you have the capacity to process every single packet, so you do not miss out on any packet. However, because you are processing every packet individually, you miss out on some important information that you could have by looking at the context between packets that belong to the same flow, packets that are going to the same destination, or that are coming from the same source. You miss out on this context. And that leads to limited accuracy when you're dealing with very complex tasks, as we would see in the rest of the presentation. So this stateless approach like I said, is the most intuitive approach. And so early work mostly focused on the stateless approaches. So in the area of stateless inference as well, we did do some work, and we proposed a solution which was for hierarchical inference in programmable switches. And the reason why we decided to go for hierarchical inference was because of the fact that in all the existing solutions, what we had was just flat inference. Okay. So if you have an inference task, you have a data set, or you have a use case, you train a model for that task, and then you map it to the switch, and then you perform inference as packets go through. So, and all of this is what we call flat classification, in the sense that you're not looking at any inherent hierarchical relationships between the different categories that you have in the data set. So the problem with this is that if the use case becomes very complex, a single classifier could become very large, that it becomes difficult for you to fit it within the limited resources that you have in the switch. And when I talk of limited resources, there are multiple constraints. It's not just the total amount of memory that you have, but something like the maximum size in bits of keys that you can use for tables. For example, if you're using a ternary match key, you can't have obviously more than 524 bits, I think, for one of the specific targets. If you're using range matches, for example, you can't have more than 40 bits, for example. So there are many constraints that you would have, which can limit the size of the model that you can implement. So if you have a very large monolithic classifier, it becomes difficult for you to encode this classifier in the programmable networking devices. However, if you look at the hierarchical relationships that exist between the categories that you have in this data set, you could be able to break down the one single task into many smaller tasks that each can be solved with a much smaller model, which together can then be represented. So look at it this way. Let's say you have a very large back and you want to fit this back in the trunk of a car. But the back on its own is not able to fit into the trunk of the car because it's too large. But if you chop it into smaller pieces, you can fit all of those smaller pieces into the same trunk of the car. So that's the idea here, if you look at it that way. And to illustrate this, I present here this device identification use case where we have multiple electronic devices, and we are trying to identify each device based on features like maybe the outlook, the sound it produces and things like that. So we could train a single model in flat classification, which tries to identify every individual device from the entire set using its own specific features. However, this model might become very large if you have so many different categories that you're trying to identify. But if we go hierarchically, we can first of all have one model which breaks down the general set into three categories. So in the first scenario, I would just be trying to tell, is this a sound device, or is this a camera, or is this a computer? So that would be a single model that is just doing classification with three categories. And then I can now have smaller models for each of those categories that now tells us, okay, given that this is a sound device, what kind of sound device is it? And then it can further classify that. So we have multiple models, but we have multiple smaller models, and together we can fit these models more efficiently in the switch. So we proposed HENA, which is basically deployed in both the ingress and egress pipeline of the programmable switch, and we implemented this on Tofino. So the idea is that in the first part of the pipeline, so in the ingress pipeline, we will implement the first stage models. Okay, so our implementation here was based on the two-stage classification. In the first stage, we would implement the code, the feature and code tables, as well as the voting table in cases where we have random forest, where we want to get the majority vote of the result of the different trees that we've implemented. We implement all of that in the first part of the pipeline. And below here, you can see how those tables look like. So for every feature here, for example, you have the source port, which was used as a feature. You would match that source port as a range match on the table, and then you will assign a given code word. Once you've concatenated all those code words, you will generate a code which you can then match by ternary match, and you can assign the result for that particular tree. So here, for example, we had 6 different features. So you would, in your apply block, you would apply all of those 6 features, and then you will apply all the code tables. In this case, we had 3 tables, 3 trees, so 3 tables for the three different trees. And then you would apply a voting table to decide on the final result based on the majority vote of the individual tree results. Once you do that, you will then assign a first classification result. So in this case, this particular packet has been classified as belonging to the class B. So when the packet is going to the egress pipeline, it knows that in the first phase of the classification, it already has the class B. So like in the diagram, in the picture I showed previously, this would be, for example, I know that this is a camera, okay? And now when it goes to the second stage, knowing that it's a camera, we can now apply the model that can distinguish cameras together, okay? So if you see here, we say if the group is 5, which in this case was for a use case where 5 was for a group of computers, for example, we can then apply the model that belongs to that particular group, and it can tell us which specific device it belongs to, or which specific device that traffic belongs to. And similarly, we have the tables for the second stage models that are also implemented in the egress pipeline. And at the end of the pipeline, we can have a final result for that particular packet. So we evaluated this using the UNSW IoT traces, where we targeted a device identification use case with 26 different IoT and non-IoT devices that we were trying to identify. In the first phase, we have a first model, a single model that runs in the ingress pipeline, which just tells us, given this traffic, from what kind of device is this traffic coming from? Is it coming from a switch or plug? Is it coming from a sensor? Is it coming from a computer? And then in the second stage, we have 5 different models that then tell us that, okay, given that this is a sensor, what sensor is it? Given that this is a camera, what camera is it? And so we had these 2-stage models that we deployed, and our results showed that with the 2-stage approach, we were able to achieve up to 11% or up to 12% gain in accuracy, specifically in the F1 score, over a 1-stage solution. So in the 1-stage solution here, basically, it's a single model that can fit within the constraints of the switch that we trained to solve this particular problem. Looking at the resources, we see that we do consume a bit more resources. That's like 3% more resources than the 1-stage model. But overall, if you look at the threshold, if you look at the trade-off between the improvement in accuracy and the little increase in the resource utilization, you would see that actually using this 2-stage approach is much of an improvement, given the trade-off of resource usage and classification accuracy. Now, despite this improvement in accuracy that we were able to get using a two-stage approach compared to a single-stage approach, the inherent limitations of stateless approaches, which is the fact that you only have stateless features and you cannot benefit from the context that you get when looking at the relationship between different packets, we then moved ahead to look at approaches where we can maintain some state so that we can benefit from this context. And how do those approaches look like? So with the stateful approach, we are doing flow level classification. So instead of classifying every packet individually, we want to classify groups of packets or flows. So what happens is, instead of just extracting packet headers and using them directly, we would extract the packet headers. Those are stateless features, which we still need in this case anyway. And then we would perform aggregations and compute statistical features from these packets. So we could get things like the sum, the minimum, the maximum, and things like that. And then, because we cannot wait until the flow expires before we perform classification, we would typically classify the flow after n packets. Okay. So n could be anything ranging from 3 to even 50 in the literature, depending on the use case and how much information you need about the flow to be able to classify it. So if we've gotten enough packets, means we've aggregated enough features over those packets, we can then perform flow level inference and then forward the packet based on the classification result that we have. Now, once we've performed that classification, we are not going to keep repeating the classification all the time. So we can store that result such that for subsequent packets that we receive belonging to that same flow, we no longer have to classify the packets again, but we can forward them directly using the inference result that we already had. Now, there is something that is important to note. The fact that we need to wait for the first n packets to be able to do inference means that for the packets that arrive before the nth packet, we cannot do inference on them because we don't yet have the features that we require to do inference. So typically, those packets will either be dropped or you would forward them using some default forwarding rule. So even though you have richer per flow features here, which can lead to higher accuracy, and the fact that in networking systems, you would generally have policies being implemented for groups of packets, not for individual packets, we still have the limitation that you would not be able to classify early packets, which would be some sort of shortcoming for this approach. So in the area of stateful inference, we proposed flow rest, which is a practical solution for stateful flow level inference. And by flow here, we are talking of groups of packets with the same 5 tuple, right? Like you have at the top of the screen. So the motivation is just a summary of what I've described previously. Given that with the stateless approaches, you do not benefit from the rich flow level features, and that in complex scenarios, your accuracy is limited by these. So with the flow level approach, we are trying to gain more context into the traffic by looking at the relationships between packets so that we can then develop policies that can be implemented network-wide at flow level. However, to be able to deploy stateful models in programmable network devices like switches, the challenge there is to be able to maintain state in these devices. Okay, so maintaining state is the main challenge that we have when dealing with stateful inference in programmable network devices. So in flow rest, what we propose is, first of all, to use stateful registers that we have available in programmable networking targets like Intertofino to compute statistical features over different packets of a flow. So we are able to compute things like the minimum, the maximum, the average, and of things like the packet size, of the interarrival time. And we can also get statistics from other things that we extract even from the transport protocol. So be it the TCP window size, be it other things like the TCP header length and things like that. So then we also have techniques that we design to be able to adapt the model to the constraints of the programmable hardware targets. So here, for example, what we are showing here was a bit selection mechanism that we developed to try to get the minimum number of bits that we need for every feature to obtain the same accuracy that we want. So for instance, we are using range matches, for example, or ternary matches to represent these features. If we have a constraint on the number of bits, let's say we don't want a feature that is more than 40 bits, and we have a timestamp that is as wide as 48 bits, how can we find the number of bits or the specific bit set that provides the best representation of the time of this timestamp? So what we do here basically is a mechanism where we look through all of those bits and determine where we can truncate effectively to extract just the most relevant portion of those features. And we made sure that FlowRest, as it was designed, was general purpose, so not tied to a specific use case. And it's a framework where you can just bring in your own data set, your own features, and you can just plug them into the flow management mechanism that we develop to be able to execute flow level inference. So here we have an overview of the FlowRest system, which I will just run over quickly for in the interest of time. So we would have of course, in the control plane part, you're going to have where you train and optimize the model for deployment, and then the actual execution of the inference, flow management, and all of that takes place in the data plane. So, in the interest of time, I'll just go over portions of the code to show you how this is implemented. So the main components are training and optimization of the model, which you have offline. Then you have the inference aware forwarding block where you filter packets to determine which ones you need to infer on. And also you determine where to forward the packet if, for example, the packet had already been classified. Okay, so if the packet is not supposed to be, is not of interest to you, you can forward it directly. If it had already been classified, you can directly determine the class from the match and action table that you would have in this block, and you can forward it directly. The interesting part, the most interesting part, is in the flow management block, where you do flow tracking using hash indices, basically computing CRC hashes to determine the flow index as well as the register index to use to store these flows. And then we have all of these flow level feature handlings where you are able to also compute the features using the register actions. And you are also able to approximate some features like the average, for example, where we would use the exponential weighted moving averages to be able to get approximations of this, as well as bit shifts, for example, also to approximate some of these features. And then you can forward packets early when they are the first few packets before the point where you're doing inference, or you can then perform inference once you have enough packets. And the model inference here basically is a set of tables, like I showed you under HENA, which you're using code tables and feature tables to represent the set of the model. Once you have the classification result, you can then send a packet digest to the controller, which can then update the different tables that you are using to store classification results so that subsequent packets can be forwarded directly. And you can also release the registers that you had to be able to use them to store other flows that might collide to this same memory locations. So in terms of the code, so basically you have different sections of the code block here, for example, where you compute the different hash indices and you get the different timestamps. Here, where you are able to manage recirculated packets. So for example, if you have hash collisions where multiple flows are hashing to the same index and one of those flows has already expired, then instead of dropping or disregarding the packets of the collided flow, you can recirculate those packets and then use them to update those memory locations in their next arrival. Then if it's the first packet of a flow, you want to be able to initialize all of those registers. And then if you have a collided flow or a flow that has timed out, then you recirculate the packet. You can also send a digest for statistical purposes. And then if you have enough packets, so if in this case, for example, if you have up to 3 packets, then you can execute the model using the different tables that represent the model, so the feature tables and the code tables. So we evaluated this over several use cases, including intrusion detection, as well as the device identification use case, similar to what we showed in HENA. And we compared the solution to several benchmarks, both stateless and also stateful benchmarks. So these are different solutions that we have in the literature that we compared FlowRest to. And if you look at comparison versus stateless solutions, just like we mentioned in the motivation, typically stateful solutions would outperform the stateless solution because of the fact that we have a lot more context in the traffic. And so we have huge performance improvements when compared to these other stateless solutions. But if we look at the comparison versus stateful solutions, you would see that for some use cases, like this anomaly detection use case where we have just 2 classes, yeah, there are less differences. So almost all of the solutions are on par because it's a pretty simple use case. So with the stateful features, we are able to obtain very high accuracies on par with the previous solutions. But for a more complex use case, based on the different optimizations that we brought in terms of, for example, getting the best set of features in terms of feature selection and even feature engineering, selecting the best portions of those features that are required to obtain the best possible results. We are also able to obtain additional improvements over existing stateful solutions as well. And in terms of resource usage, if we look at something like TCAM, we consume, so Flores is the red star, we consume just about the same amount of TCAM as the other solutions because we are using similar mapping techniques. But then if we look at something like SRAM, for example, we consume more than stateless solution, obviously, because the stateless solutions store nothing. So SRAM, where we store all the different features in the registers, we definitely consume more, as well as NetBeacon, which is also a stateful solution. But if we look at TCAM in general, we are doing quite well compared to NetBeacon, for example. Here we have much less TCAM, which means that indeed the trade-off still between the accuracy and the memory consumption is still a quite reasonable one, and we can discuss more on this if there are questions. So let me, I think it's 39 already, so let me see if I can go to the other parts. So now, so this, having spoken about the stateful features, so like I mentioned, in the stateless approach, we have the benefit that we are able to classify all the packets, but we are limited in terms of accuracy because we don't use rich flow level features. In the stateful approach, we are not able to classify all of the packets because we are missing the first few packets before we get all of the features calculated. But then we have better accuracy because we are using richer features. So why not come up with an approach where instead of just classifying instead of just classifying the flows after we have had enough features, we can also classify the early packets. And that's where the joint or hybrid approach comes in. So for the first N packets, instead of just doing default forwarding, we bring those packets back into our joint model and we classify them using only the stateless features that they have. So only the features extracted directly from their packet header. And then if we have enough features, so if we have computed the flow level features which we required, then we can do the actual flow level inference like we have here, and then subsequent packets coming can then be forwarded. So if you can use the benefits of both approaches, you would be able to get some kind of the best of both worlds, which is what brings us to the hybrid approach here. And the motivation for doing hybrid stateful, stateless inference here is that we can benefit from both the fact that we can get all the packets classified, and we can also use the rich flow level statistics that we have from stateful flow level features. And here we present some statistics that we found by analyzing some of the publicly available data sets that we had. So these numbers specifically were from the Ton IoT data set from UNSW in Australia. And we found that if we are looking at, since most of the literature, if you're talking of a flow, right, you want to have at least two packets from it. So not just a single packet. Let's say if you consider a situation where you do inference after the first two packets, up to where you do inference after the first 50 packets, you will realize that for the Ton IoT dataset, this just either the first two packets only would account to about 67% of the flow length for most of the flows that you had there. So this dataset had a lot of short flows. Basically, this is what this means. Such that if you consider up to 50 packets, then for most of the flows, you would have already covered about 98% of the flow length. So imagine that if you've already covered more than 60% of the flow length by looking at the first 2 or 3 packets, if you don't classify all of these packets because you're still waiting to compute flow level features, then you miss out on the larger part of the flow. So being able to classify all of the packets of the flow is therefore relevant, which is what, one of the motivations of using this hybrid approach. So if we are able to introduce a hybrid approach where we are able to account for all of the packets while using the flow level features still, then we can get the best of both worlds. And previously, this has been attempted in previous solutions like NetBeacon, where we say, okay, since we want to be able to classify everything, let's deploy multiple models. Let's have a model where when a packet comes, if it is not yet up to the nth packet where we want to do flow level inference, we are going to classify it using a packet level model that exists in the networking hardware. If we already have enough features, then we can classify it using a stateful model that also exists there. And we can also have a model that distinguishes between when to use only the stateless model or when to use the stateful model. This works very well, but the disadvantage here is that you have to deploy multiple models. And when you deploy multiple models, you are increasing the memory consumption that you have in the device. Of course, we have limited memory in these devices. So to be able to optimize our memory consumption, we introduce Jewel, which is basically a single model trained on both stateless and stateful features to be able to perform joint inference. And the idea is that for the first n packets over which we are training the model, for the n-1 packets, we have their stateless features, and then we assign arbitrary numbers to their stateful features. So let's say 0, for example. And then for the nth packet, which in this case is the fourth packet, we have the full set of features, both the stateful and the stateless. So the model will be trained having in mind that for the first n-1 packets, we don't know what the stateful features are, but we know the stateful features. And then we assign weights also, so that the stateful feature which we use to the fourth packet or the nth packet which we use to perform stateful inference has as much weight as all the packets before it that used only stateless features, in order to have a balance between the weight of the stateful and the stateless features. And we found that with this approach, we were able to obtain accurate models that can classify both packets and flows depending on what point in the life of the flow we are. So it's the architecture is quite similar to FlowRest, but the key difference is in the way the inference is done. So the way the inference is done is that in one case, when you have few packets, you can do inference using only the packet level features. And then in the case where you have all the features, you can do inference using the entire set of features. So that's the main difference that you have. Then again, there are other optimizations in terms of how the flows are managed, in terms of how collisions are managed, in terms of how you update the different tables and registers that you have in your system and things like that. But the core of the difference is in how you execute the flow level model with either only stateful features, only stateless features rather, or with both stateless and stateful features. So the evaluation settings here are similar to those of FlowRest. So we still run this on Tofino, and we also test 4 different use cases, ranging from intrusion detection to IoT device classification. And we compare to several benchmarks as well, both stateful and stateless. We find that overall, with the hybrid approach, we are able to have between 2 and 5% improvement over existing solutions that target either stateless or stateful inference, or even hybrid, which is the case for NetBeacon. And when looking at 2 to 5% improvement in accuracy over these solutions. And when looking at resource usage, it is even more interesting, because when we look at the other hybrid approach that exists, like NetBeacon, you see that because we are deploying so many models at once, the memory consumption is very high. And if you look at TCAM, for example, which is the most expensive resource as far as we are concerned, the consumption here is very high. Whereas for us, because we have just a single model, the TCAM consumption is quite low and is very much on par with what we have in these other solutions, since we use similar mapping techniques. And so in summary, to kind of capture what we've learned, the lessons that we've learned going through all of these approaches is that there is no, you can't just say, oh, always use this approach. So it will depend on what use case you have in front of you and what you need for that particular use case. So if you're dealing with something which is simple enough and you want to be able to cover all packets and you want early decisions, go for a stateless approach. If you're looking for something where you want very high accuracy, and it's okay, the flows are very long, you can miss the early packets, it doesn't matter, then you can go for a simple stateful approach like FlowRest. But if you want a situation where you want to capture all the packets, accuracy is also very important, and you are able to deal with a little bit more complexity or with a little bit more memory utilization, then you can go for a hybrid approach like Jewel. And in the literature nowadays, also there's been other solutions that have been developed across these different approaches to show how we can exploit different ones in different scenarios. So in terms of ongoing and future work, currently we are diversifying the inference targets that we've been using. I'm currently working with the Intel infrastructure processing units, and we're also looking at what we can do with Bluefield 2 and Bluefield 3 as well, which just got recently. And also there's a lot of work in the community on these areas. I've been looking at a literature too in that space. And then we're looking at also distributed inference and in heterogeneous settings as well. My colleagues just published a paper recently in Infocom as well on distributed inference. And we're also looking at going one step beyond that. So not just having static models, but also being able to detect drift and update these models at runtime and, have online learning included as well. And we're looking at other use cases. With Oxford, we've been collaborating on some use case for healthcare monitoring, deploying some models on IoT gateways in Internet of Medical Things environments. We're also looking at other aspects in terms of acceleration, like KV cache acceleration and other use cases like that. So there's a lot of interesting use cases that are coming up, and we are also exploring that space. So in general, we would say that what in-network machine learning is enabling for us is, high-speed intelligence in the network. And a lot of work is being done in this area. We are getting a lot of interest in this area, and we hope that these solutions will continue to lay the groundwork for in-network inference as a potent tool for automation in networking. And we hope that the future steps will, help us to get closer to a more seamless integration of machine learning into networks. And talking about that, I would like to end with this quote from Bruce Davey. So he said, just as self-driving cars have been just a few years away for more than a few years, I suspect that automating the management of physical networks is going to remain out of reach for most of us for a while longer. So yes, there's a lot of work that has been done on this area. And I guess in-network machine learning is contributing to this aspect of automating networks, but we are not there yet. So there is still a lot that is being done from other angles as well. And we hope to continue to contribute to this with this aspect of in-network machine learning. So just to recognize my collaborators who worked with me throughout my PhD as well, my supervisor, Marco Fiore, my postdoc, Michele, and Beza as well, who've been working with me throughout these past 4 years. And all of the publications that we mentioned in this work, you can find them there. And so thank you very much for your attention, and I'll be happy to take any questions that you might have.
Thank you so much, Aristide, for your presentation. It was very interesting and very detailed. I really enjoyed it. And thank you again for joining the P4 Developer Days and presented it. I don't know if there are some questions from the audience. Yes. Okay, so from Andrea asked, for what concern the possible feature that can be used in flow-based classification, which statistics can be used?
So regarding the features, the easiest are usually the maximum, minimum, and the total, for example, right? Because you can easily sum, you can easily find the maximum, you can easily find the minimum. Now, you can also find the average, for example, especially when you are dealing with powers of 2. So for example, if you're working with the first 4 packets or the first 8 packets, then calculating the average is equivalent to doing a bit shift. So you can use bit shifts to approximate averages. So that enables you to be able to get means, which means you can also calculate the average. And I think I've not used the variance particularly, but I think I've also seen others who've been able to approximate even the variance. So there are techniques to be able to do these approximations, but minimums, maximums, totals, averages, things like that. And then in addition to those, you also have the stateless features, which are just the statistics that you get from the packet headers.
Thank you for the answer. Salvatore, you can go with your question.
I was trying to switch on the camera. Give me a sec, maybe.
Yeah. Hi, Salvatore.
I don't know if you can see me. Hello.
Yes.
Nice to see you. Nice to see you, Aristide. Hope you're doing well. Thank you so much for the presentation. I really enjoyed this line of work. I would like to ask a question about what's next. It seems like the state-of-the-art work has sort of pushed the boundaries of how much can we optimize models and features on a data plane of a PISA-based switch architecture. So do you see still more works coming that will propose further optimizations of, I don't know, the model themselves or the feature that you need for this decision tree-based models? Or you think we have pushed the boundary, at a point that there is nothing more to do?
Yeah. Okay, thank you very much, Salvatore. So I personally, I'm never confident enough to say we've pushed the boundary to the point where we can no longer advance, because even as very recently, I think it was in the most recent NSDI, there's a paper I think called Split DT, which talks about how you can split decision trees, and better represent them on the data plane. So I would say it's really advancing, and there's a lot of interesting work that has gone even beyond what we've done. So there's some work already on drift detection and implementing also online learning to be able to update these decision trees in real time while you're doing inference on the network. There is this idea also of distributing them and things like that. So I think most of the work that I think would be coming will be works that are building on what exists, but then optimizing how efficiently we can deploy them, how better we can use the resources that are available, so that a lot more can be done beyond just the inference. And also maybe being able to use more features. So can we be able to compute more features? Can we use other devices to assist things like the switch? So the switch has very high throughput, but maybe the computation power is not strong enough. So can we compute some features on the smart NIC, for example? Can we use the control plane for some of the tasks and have a more tighter collaboration between what we are doing in the data plane and the control plane? So I think there'll be a lot of optimizations coming in these different aspects.
Thank you. I don't know if I may ask a follow-up, Davide.
Go for it. Okay. Go for it.
Thank you very much, Aristide. So you said something very interesting that I want to ask a follow-up question, which you said, okay, using more features, but you have this inherent trade-off. Computing more features on such a target basically sort of limits implicitly the size of the model. Basically, you have a tension there. It's true that you can compute more features, but then this sort of create additional constraints into the model that you can deploy. How do you see solutions coming that can address this problem? If you have an idea, how can we use more compute and use more features while we do not restrict the size of the model that we want to deploy on the switch, for example?
Yeah. That's a really nice follow-up. And I think the most viable solution, which I'm seeing being exploited for this, is distribution. So for the distribution, this is one of the key things that it's enabling. So there's the different ways that people have approached for the distribution. There's those that have said, okay, let's do distribution by saying the first node is going to do only feature extraction and computation. So that way you can dedicate as much compute as you want on that node just for feature extraction. And then you have the next node, which is doing just inference. You have another node, which is doing just voting, and so on. So maybe then the question comes again, then, okay, if you have this distribution, do you have an additional protocol that can enable all of these distributed pieces of your model to communicate? Those are other questions that you need to answer. And then there's those who say, okay, you can do some kind of service function chaining so that this becomes like some kind of service that runs on multiple nodes and stuff like that. So I think distribution is key to this. And then, maybe doing some heterogeneity, like using other targets as well in association. This might help.
I agree on both. Thank you for the answer.
Okay. Thank you.
I don't know if there are any questions from the audience. Okay, Andrea has a question. So reducing the feature size as shown in flow rest allow us to have a feature which have a size that is right for the code word used for the classification. So that fits the maximum size for the match action table of the architecture.
Yes, that's correct. That's
Okay.
correct. Is that the end of the question?
Yeah, it's the end of the question. It's
Yes. Yes, that's correct. So I think we had to do this because when we started working on this, we were working with Tofino, and we were also using range matches for some of the features. And then with the range match, we have that limitation now. So you have a total of 40 bits, which means each part of the match should be not more than 20 bits, I think. So if you have a timestamp that is for 48 bits and you're already approximating it to 32 bits in the target, and you want to use this as a feature, then offline, we try to find, okay, since we cannot use all of the 32 bits, what portion of this bit of these 32 bits is the most important? So sometimes we find that only the top 4 bits of this timestamp are actually relevant for the classification tag. Sometimes it's up to 15 bits, sometimes up to 16 bits. And then we take that bit slice and it's what we use as the feature. So when we get the timestamp from the switch, we are only going to take the first X bits and put in our model because that's what we've identified offline as being the relevant part for classification. So yes, the main idea is to help us compress the bit size and enable it fit the hardware target that we are dealing with. So yeah, that's a good understanding.
They asked a follow-up question, which is, are there other techniques that can be used?
Yes, there are other techniques, and if I was to repeat Flores today, for example, I will not use range matches for these things because again, your range matches are not available on all targets. So if you're not on Tofino, maybe you only have ternary matches. But then there are techniques to convert range matches to ternary matches. So that's one thing I would do, convert these range matches to ternary matches. That way you don't have to approximate this, because if it's a ternary match, I think you can have up to 524 bits in Tofino for the key.
Thank you so much. Ahmed, do you have a question? Please go ahead.
Yes, thank you so much for the presentation and the really impressive work you have done. I have a question. Is there any studies or statistics for your models in actual networking architectures? Because I see from the use case from the testbed, it's just 2 servers with a couple of DPUs or SmartNICs. Is there any studies that shows the effect of the ML inference on the network behavior in general, in terms of the jitter, for example, or the delays, or the performance of the effect could happen in multiple node network architectures.
So yeah, thank you for the question. So unfortunately, we don't have like a very large scale system where we can run this test. So we have just 5 in my lab. We have just 5 of these switches. So what we can tell you is that okay, if we have a scenario where we have 3 different switches and we measure like what is the processing latency on each one, and we know that okay, we are able to do inference with just a few hundred nanoseconds of latency. So the understanding is that wherever you have this node in your network, as if you're running this particular P4 program on that node, you should be able to do whatever you're doing at a few hundred nanoseconds of latency. So then your total latency then you would have to then add whichever latency is being introduced again, by all the other components that you have along the line. So unfortunately, we've not had any large scale evaluation, but since the hardware that we are using, so this Intel Tofino switches and all of these are production grade hardware. So you would expect that if you find this hardware, in a production setting, running this program, the behavior should be deterministic. You should be able to know that your latency will be a few hundreds of nanoseconds. You would be able to have, line rate performance. And so that's the minimum, that's the maximum we can do, in our, experimental environment. But yeah, hopefully we have more large scale evaluations that consider larger settings. I know that there used to be some I used to see that there was like the use of programmable switches for different tasks in Google as well, but not for not for specifically for in-network machine learning. So I've not seen any, exact results on that on a large scale.
Thank you for the answer. I think that we can close here. So first of all, thank you again, Aristide, for joining the P4 Developer Days. It was a pleasure to have you here. And then the next P4 Developer Days session will be the 4th of February, and it's it's going to be a presentation made by a vendor that is iWave, and is going to present his P4 SmartNIC. And the title of the presentation is Programmable Data Planes for the Cloud Era, harnessing P4 on FPGA-based SmartNICs. So see you on February, and have a nice day. Bye.